This video is a lecture on related rates, which is an interesting application of derivatives. Now, this talks about the chain rule and more specifically implicit differentiation. Now, unlike the lecture on implicit differentiation, where y was in terms of x, this, every variable is going to be in terms of t. T, obviously, in physics, used to represent time. So this is, before the last section, if you took the derivative d dx of x cubed, that would just be 3x squared. But everything here is d dt. Nothing will be anything but d dt here. And that means, so every time you take the derivative of something, take the derivative the normal way, and then put d whatever dt. This one I don't use the prime notation as much. I prefer to write out the dx or whatever d something dt. But I guess, if you want to write it as prime yourself, I guess that's fine. 3x squared x prime, 4y cubed y prime, I guess that would be okay, as long as you realize that all those primes are with respect to t. So let's look at a very basic related rate equation. So when it says find the related rate equation, what that means is you're differentiating with respect to t. Now then we'll see what kind of applications we'll use this for here shortly, but at least know what that means. You're finding the derivative with respect to t. So for this equation, x squared plus y squared equals 16. The derivative of x squared would be 2x dx dt. The derivative of y squared would be 2y dy dt equals 0. And that's it. So this one's, unlike the other implicit differentiation stuff we were doing, you don't have to isolate a variable. You're not having to algebraically solve in the equation form for a certain variable. Now, when we start doing some application problems here, you'll be solving when you have numbers. So there's four things here: x, dx, dt, y, dy, dt. If we have any three of those four bits of information, we can solve whatever we're looking for and find that value. But what I'm trying to say is that we don't have to take an equation and write it out algebraically in terms of one of the variables. You leave it like that, that's it. Now over here, it's because you see that you could divide if you wanted to. It's not wrong if you don't. But if you wanted to divide everything by 2 here, you would see that it reduces to x and the y. But it's okay. So it's just a reduced form. But obviously this first one is equivalent. Now here's one for the volume of a sphere. Now, people often ask me, do you have to know all these kind of formulas? Absolutely not. So don't panic about that. I always provide those for the students. I would give the v equals 4/3 pi r cubed. You don't have to know that. I'm just telling you that it's the volume of a sphere. So don't worry about having to know those. I'll show you some things that are some basic stuff you should probably know. I think most people would have no trouble, but not these. You don't have to have these memorized. So the derivative of v is dv dt, and then you only have one variable, of course, because pi is a number. So the derivative of r cubed would be 3r squared dr dt. Cancel the 3's. So technically then the related rate equation would be dv dt equals 4 pi r squared dr dt. I've got a picture of a sphere and a cylinder down there. Next one is a right circular cylinder. Okay, so now we have to be careful on this one because we have two variables multiplied together. So just like we did in the implicit differentiation section, if they're multiplied together, product rule is required. So we have to do a product rule for now. Because pi is a number, I just keep pi with the r squared. Instead of holding the pi out there and then distributing it through later, I just keep pi with the r, the first thing I see there, and just keep it together. So the derivative, if you do f prime g like I like to do, so the derivative of pi r squared would be 2 pi r dr dt, because the derivative of r squared would be 2r dr dt. So you see how it's always some d something dt every time. And now over here, the f would remain the same, pi r squared. You take the derivative of h, which essentially is 1, but it's 1 either h prime or dh dt. Kind of like the left side for the v was dv dt. So the derivative of h by itself would be dh dt. Now this one has actually 5 variables. dv dt is all the dv dt, dr dt, dh dt, and then h and r. So if we wanted to solve a problem, which we will shortly here, as long as you have enough information to represent 4 of those things, you can solve numerically for the 5th. Looks like I did that circle one again. I don't know why that came up twice, but that's okay. I'll leave it there. But I think I wanted to apply it to this specific example right here. Now, you can look at this example of like a point moving around a circle, at a certain rate with respect to time. Now, so there's our related rate equation. I've already explained that one, so I won't do that one again. Well, you could get rid of the 2's if you wanted to. Now, dy dt, find dy dt when x is 3 and y equals 4, dx dt equals 8. Now, I don't have units here, but, 8 could be like 8 inches per second or 8 feet per second. These rates are always going to be something like, for the linear rates, of course, volume would be, like inches something cubed per second, and area would be something squared per second. You're not going to have to worry about it, units that much on a test, I don't think. But obviously, when you take, science and engineering type classes, I mean, units are very, very important. But I didn't assign units to this one either, anyway. So I found the point 3, 4. And I'm showing that the point would be moving in the direction of the green arrow. Now, this is not important because you can solve it without knowing that. But I'm going to explain to you why I drew it like that and why it's moving that direction. But you could solve it without ever even drawing that graph, because that's usually a very common question. How do you know it's going that way? Well, dx dt equals 8, positive 8. That's the key, positive here versus negative. If that point is sitting here, and it's either could be moving to the left or moving to the right, but in the position it's right now, if it's moving in such a way that dx dt is positive, meaning x is increasing, it would have to move right. Because on this particular location, as it moves right, it's going increasing, x is increasing. So that's how I knew it was going that direction. And we'll see if the dy dt matches that whenever I'm done. So I put in 3 for x, 4 for y. Dy dt is our unknown. So that's a pretty simple equation once you get the numbers in there. And to solve for the dy dt is just like solving for a variable by itself. You get negative 6. Okay, well that also backs up my direction of that arrow, because from that point in the first quadrant, as it's moving to the right, it's also moving down, isn't it? So if it's moving down, that means y is decreasing, so it would have a rate of change of negative. So that's how you look at this. So, dx dt is positive because x is increasing as it goes to the right, and then dy dt is negative because it's increasing as it's going down. Once again, you're not just going to sketch that though, but let's look at this one. I don't know why I made the arrow a different color there. That's no reason. Put in this point. Now it's giving us dy dt, and it wants us to find dx dt. No problem. So if dy dt is negative 2, from this location in the second quadrant, I know that the point has to be going to the left. Because if that point was going starting at that circle and moving to the right, dy dt would have to be positive because when you're in quadrant 2 and it's moving to the right, it's going up. So that's how I know I had to make it go down that way. And even before I solved this problem, which once again is not critical, you can solve it, not worry about any of this. As you can see from this location in the second quadrant, as it goes down, x is also going left, which means in this case, dx dt needs to also be a negative number. So let's see if that works out mathematically. So you plug in the numbers into the related rate equation from up here and solve for dx dt, and we get negative. So in that particular case, they are both negative. Down and to the left. All right. Okay, let's say we have a cube here. And all edges of a cube are expanding at a rate of 6 centimeters per second. So it's some sort of like growing cube. It could be like a horror movie, Attack of the Killer Cube. You could also do this for like melting ice and have the rates be decreasing as it's melting. So at what rate is the volume changing when each edge is exactly 2 centimeters long, and then when it's 10 centimeters long, what is the rate the volume is changing at that point in time, the instantaneous rate? Now this is one where, like I said, this is the other formulas, but I would hope that you have enough skill that you could come up with, you don't have to use letter X per se, but I'm certain you could come up with this equation, x cubed, without being given, you don't even need the picture, but there's one I would expect a student to be able to come up with, because it's not that hard. If it's x by x by x, it's x cubed. But you can use a different letter if you want to. That's no problem. So volume is x cubed. So here's a shorthand for related rate equation. dv dt on the left side, and on the right side would be 3x squared dx dt. And then the dx dt is 6 in both scenarios. So the cube is constantly growing at a rate of 6 centimeters per second. Had that said decreasing, we would have just made the number negative. So anytime you see decreasing, you have to realize it's negative. Or it could just say the rate's changing at a negative amount, like my example up here. So and changing at a negative is the same thing as verbally saying decrease. So like for this one up here, if it would have been in words, you could have said y is decreasing at 2 whatever units per second or something. Then it would have been negative. So, but here, so if they use words, decreasing, if the number's positive, just make it negative. So we plug it in here, so we're looking for dv dt. You're not always solving for what's on the left side. You'll see an example of that in a minute. Keep that in mind. Don't say, automatically solving for left. We could have been solving for dx dt, depending on what we were given. But we weren't in this case. So put in 2 for x, 6 for dx dt. And that means the rate of change at the volume, when it's at 2 centimeters, it's increasing at 72 cubic centimeters per second. And then for the next one you put in 10, it's 1800 cubic centimeters per second. So naturally the rate of change of the volume would be a lot larger, because the actual volume of the cube is going to be a lot larger. So therefore its rate of change would be larger. All right, so now here we have a balloon, spherical balloon, so it's a sphere. It's being inflated at a rate of 600 cubic centimeters per minute. At what rate is the radius changing when the radius is 20 centimeters? So let's look at the related rate equation there for a second, which is easy enough. We did this one earlier. So dv dt equals 4 pi, because the 3 kills the 3 here, 4 pi r squared dr dt. Now, the million-dollar question is, how do we know what variable we're solving for? Well, there's 2 ways you can tell. The question itself is what it's asking. At what rate is the radius changing when the radius is 20 centimeters? Radius changing, that means dr dt. They are giving us the dv dt. you might not say it, but the units tell us. It's cubic centimeters per minute, 600 cubic centimeters per minute. That is a volume measure, a volume rate. So that's telling you it's the volume. So that's how you know. So that's how I knew that dV dt was 600. But mainly the question itself tells you what we're asking. R is 20. So you see, for this problem, we're not solving for the left side. That goes in with what I was saying about the last problem. Don't always assume you're solving for the left side. So I put 600 here. I have 4 pi and put in 20 for the r, so it's 20 right there, given squared, and then dr dt. That's our unknown. That's the keys. We have all our so 600 then ends up being 1600 pi. So you divide it, reduces to 3 over 8 pi. Now this is kind of interesting, which isn't too bad if it's written in exact terms like that. But let's just say you had to get a decimal answer. Here's a very common mistake that students do. The mistake they make actually is the middle of these 3 things I wrote here. What I have up at the top is correct. Now the middle one looks like it's correct. It's tricky because you type that in the calculator, that looks right. It's 3 divided by 8 pi, but that's not what the calculator thinks. You have to use parentheses to keep everything on the bottom. Now the reason why I did this part at the bottom was to show you that the middle answer is the same as the bottom answer. So really 3 over 8 with a pi next to it is really the same thing as 3 pi over 8. See how they match? Yeah, that middle one just looks like it would be right visually, but it is absolutely not right because the pi is not attached to the 8 unless parentheses tell you it is. Okay, so I don't know if that's going to come up anywhere, but it's good to know, I think, mathematically that, okay, because you're trying to get a decimal answer, it'd be pretty frustrating if you did this problem right, and you got to this point and couldn't find the answer. The correct multiple choice answer because of the calculator issue. Okay. Now, so we worked this one out earlier. Check that. So I'm not going to derive it again, but here it is. Let's we did it right up here. Where was it? Yeah, see, there it is. The right circular cylinder. So I just copied it and brought it down to do an example. And we'll not have a picture there, obviously, but now let's read this one. This one could be kind of interesting. Find the rate at which the height is changing. So I'm saying finding the rate. So the rate could be negative or positive. It just depends on the scenario. Because you could have that cylinder could be a situation where the radius could be increasing at the same time as the height is decreasing. That's certainly possible. So the height is changing. I'm allowing for the possibility of positive or negative. Obviously, it's not saying if it says find at what rate it's increasing, that kind of gives you away that it's going to be positive. But it's changing means either way. So the volume is increasing at 30 cubic inches per second, and the radius is decreasing at 5 inches per second. When the radius is 10 inches and the height is 14 inches, and we're going to figure out what rate our height is changing. dH dt, right here. I've seen a problem. I've had it on my exam reviews. I think I removed it. I hope I did, but if this comes up, at least you'll know that where I had a problem like this, and it didn't mention anything about the volume, and it looked like, well, it had some missing information. It should have said something about this, but the fact that it didn't, it actually means that the volume is not changing, which means that's actually possible to have that happen. Let's say if the radius was increasing at a certain amount that offsetted a height decrease. So if the height was going down at a certain number where the radius was increasing at a certain number, you could actually have a situation to where the volume was not changing. But that was kind of, I thought, was poor form. It could at least said note, but it could have said that the volume is not changing, therefore you could have known that dV dt equals 0. I would never put that on on my review in the past, and I think I've removed it, but I'm not sure. But I would have it in my worked out solution, so then you would see that it was zero if that was the case. But obviously, if both of these variables are increasing, then your volume is going to be increasing, of course. But because we have two variables, they can kind of neutralize each other. Unlike a sphere, if the radius is increasing in a sphere, the volume is increasing. If the radius is decreasing, the volume is decreasing. But you can have two, like I said, two variables working against each other. Heck, you can have decreasing radius and increasing height, and it may be no change in the volume. All right, anyway, enough of that. So, like I said, I don't like to solve these algebraically. I just put the numbers in, then solve for it. You don't need to rearrange all these variables. Much easier to plug all the numbers in. So you see that dv dt is 30. Okay, this is important right here. This is very important. dr dt is, it says the word decreasing. So it's decreasing at 5 inches per second. That makes it negative. So very important there. Radius is 10. Height's 14. And so I just kind of plugged everything in from up here. So you can see if everything fits. I just factor out a pi here for some reason. I don't know why I did that. I don't think you don't have to. 2 is from here. 10 is the r. dr dt right there is negative 5. H is 14. R squared will be 10 squared, and dh dt is your unknown. So I divided by pi. That all worked out in the middle there to be negative 1400. That's plus 100 dh dt. So I came up with this weird looking answer here, which this kind of problem, I'm a big fan of exact answers on my test, but for face-to-face classes, so I want the answer exact. And I might make an exception for this problem. Let's just say you get the decimal answer. So something like this, I would expect the answer to be decimal. So you see, I just kind of put that all in there. So, okay, so the radius is decreasing, but the height is increasing at such a rate, 14.1 inches per second, that the volume will still be increasing. So this is one where, so the radius is decreasing until eventually, obviously this can't go on forever. It's going to eventually no longer be a cylinder. But at least for a little while, it'll decrease while the height's going up at a much quicker rate, which is allowing the volume to increase. At least until it vaporizes, I guess. Oh, I just chose one decimal place there, but that's the least of your problem. Now, the classic ladder problem. This is very common, right triangles. So we just got through seeing, various famous shapes like cylinders and spheres and things like that. Those are good. And but the ladder problem and right triangle related rates are very important and commonly used. I've been known to put this on a test and on the exam, and I've done it in the final before too. Now I'm using now this problem. I'm assuming the ladder sliding down the wall. You could actually, I've seen problems with where it tells you that, let's say instead of a ladder, it was just like a beam, some sort of wooden beam or something, and they're pulling it up the wall, so the X could be going in and the Y could be going up. But if it's the ladder, you're looking at it as if the ladder is sliding away from the wall and it's coming down the wall across the top. So we're saying the ladder is just kind of sliding down the wall. And hopefully we're not on that ladder as it crashes to the ground, because I don't think we would really care at what rate it's changing if we're on that ladder. Now, just treat this as sort of a Pythagorean deal here. So I just used theoretically could use any letters you wanted, but I think I chose Z. If you want to do something other than Z for the hypotenuse, that's fine. But I think X and Y are good because of the X and Y axis. That would just be less likely to be confusing. All right, so we have x squared plus y squared equals z squared, our good old friend Pythagorean theorem. Okay, easy enough to take the derivative, so it's 2x dx dt plus 2y dy dt plus 2z dz dt. Okay, so that's the $1,000,000 question. Stewie's addressing it right here. Maybe I should have stopped there so you couldn't see that. That's okay. All right, well, for some reason I just magically crossed out dz dt like it didn't belong. Why in the world did I do that? Sort of goes back to that problem I was talking about, if it told you that the volume wasn't changing, in that right cylinder. But anyway, all right, interrelated rate equation, and it's not just these kind of problems, but it can be others too. If there's a variable for whatever reason that's not going to be changing in the problem throughout the process, if it does not change, it would have a rate of change of 0. Kind of makes sense, doesn't it? If it's not changing, it would be a rate of change, related rate of change of 0. Because as that ladder slides down the wall, y is changing. The height's changing. As it goes away from the wall, x is changing. But the ladder's not. We're assuming it's a fixed length ladder here that's not, expanding and getting longer. So, if the ladder was 50 feet long, it's going to stay 50 feet long even as it's moving down and out. So if the variable doesn't change, its rate will be 0. So that's how I knew that was going to be 0. That doesn't mean that z is completely useless, because you're going to see we're going to need Pythagorean theorem. Sometimes it'll give us x and y, and we have to use this equation to get the value for z. Well, or we'll have z and x. Have to find either x or y. Obviously, we don't really need z, because z will be given. The ladder length will be given to us. So we use it for this purpose of finding either x or y. All right, so this is the related rate equation. You could divide by 2's if you wanted to. Some people do, some people don't. So if you felt like canceling those out, you could. If you want to leave them, that's terrific. All right. So now Stewie's yelling at us. Any variable that doesn't change will have a rate of change of 0. So that's what I was just saying. All right, let's try a ladder problem out here. Suppose we have a ladder that's 17 feet long. It's sliding down the wall at a rate of 4 feet per second. At what rate is the ladder sliding down the wall when the base of the ladder is 8 feet away from the wall? Okay. So obviously I'll scroll down here in a second, but ladder sliding down the wall, that would be down the y-axis at 4 feet per second. So if it's going down, it's going to have a rate of change that's negative. So that would be very important in our solution here, that we realize that's a negative. And then when it's 8 feet away from the wall, that's going to be x. So x will be 8. The ladder length, the z, will be 17. So here's what I was telling you, that even though the dx, even though the right side turns to 0, it doesn't make that 17 completely obsolete, because we need it right here in the Pythagorean equation. We need it to get the value of y. So like I said, sometimes you'll have the x will be given to you and you solve for y, or the y will be given to you and you solve for x. So we don't just totally trash the length of the ladder there. We still need it. And I purposely picked out a Pythagorean problem where what they call a Pythagorean triple. Pythagorean triple means where it's 3 integer values. I mean, the most famous one is 3, 4, 5, but this is one of them. 8, 15, 17 is another one. 5, 12, 13. Okay, I'll quit rambling about that there, but that's what a Pythagorean triple means. They're all integer values. Okay, this one I divided by the 2's. Okay, I got rid of the 2's, because it's still 0 on the right side. So keep the 2's, ditch the 2's, whatever makes you happy. Mathematically, it'll still work out. So I put the 8 in for the x. dx dt is my unknown. At what rate is the ladder sliding away from the wall? Right there. And you can tell that's going to be a positive answer, right? It's going to the right. So, all right. So plus 15, which is the y that we just found right here, and dy dt is negative 4, as I mentioned earlier, equals to 0. So you solve that equation pretty easy. So 60 divided by 8, 7.5 feet per second. So it's going down the wall at 4 feet per second. It's going away from the wall at 7.5 feet per second. That's not too bad. Now, sometimes this part can be a little bit frustrating for students. In my face-to-face classes, I've given like 2-part problems. sometimes where one of them will be to define what we just did, and then bring trig into the game here. Um, let's find the rate of change or the angle formed by the ladder and the wall. So that would be up here. I've labeled theta. So is the ladder sliding out at what rate? In radians. We do all these problems in radians. You could convert them to degrees, multiply by 180 divided by pi if you wanted to for your own amusement. But you don't have to, of course, but these answers will always be radians per second. Now, let's see. Here's the thought process here. Because obviously if you have an angle theta here, you're going to need some sort of trig function. And you've got 6 possible options. Now, what you want to do is you want to use a trig function that takes the ladder into consideration, because if it takes anything that's a fixed length, if it is a fixed length, you want to take that into consideration. So I'm writing this as sine of theta equals x over 17. You can't really use the 8. You can't use those numbers. You have, because it's a variable, it changes. You have to use the variable. So if I use sine, it would be x over 17. That's the best one. Because somebody's, I've always been asked, well, why can I just use tangent? Well, let's just say if you did use tangent, because x and y are both changing variables, you would literally have to write your equation like that, like this. So I'm just trying to do this in the easiest, but there are certain problems where the tangent might be useful, but not for the latter problem. I'm going to show you a different kind of right triangle problem in a minute. But because x and y don't change, you have to use their variables. So from up at the top, it'd be opposite, which is x. You have to make it x over y. You have to do it that way. Which means you get to do a quotient rule. So you got to do a quotient rule, and it's just more difficult. And you can still get it right, but it's just way more trouble. Now you could have also done, for this one, cosine would have worked well too. You could have done cosine of theta. Cosine of theta would equal y. You have to use the variable y over 17. So I could either done a sine of x over 17 and cosine of y over 17. So those are the two best choices. Either one would have worked. I chose sine. So this is your related rate equation for the angle. Sine of theta equals x over 17. Which is the same thing as 1 over 17 times x. Sometimes I'll see students take problems like this, the derivative, and actually do the quotient rule or something like that, which is you could do, but it's just if you just like adding more work to what you're doing. But it's just x over a number. It's the same thing as 1 over 17 times x. So let's make it easier. So the derivative of sine of theta with respect to t will be cos of theta d theta dt. Because that's what we're solving for, is d theta dt. The rate of change in the angle will be d theta dt. So just take the derivative and stick the d theta dt. Now on the right side, the derivative of 1/17th x will be 1 over 17. But remember, in this kind of idea, the derivative of x is not doesn't just go away. It's dx dt. It's like obviously if we were back in one of the earlier chapters and somebody said, "Oh, find the derivative of 1 over 17 times x," it would just be 1 over 17 and you'd be done. But now we have this implicit idea, so you have to put dx dt right here. So we have 3 variables: cos theta, d theta dt, dx dt. Now, here's where you take the numbers into consideration. This is where you use all numbers are in fair play, and just the ones you need. You only need 2 of them. So you have to, like I said, on the right side there, you have to use variables whenever you see, we had to get that dx dt because it's a rate of change. But cosine of theta literally is just taking it off your triangle. Cosine of theta would be 15 divided by 17. D theta dt is my unknown. So we have a 1 over 17 here. Dx dt is we found that right there, 7.5. So you put 7.5, looks like I canceled the 17s. Pretty basic, simple algebra here. I'm sure you don't have to do it exactly the way I did it, but you should come up with 0.5 radians per second. So if you multiply 0.5 times 180 over pi, that would tell you some sort of degree measure if you were just really curious. But it's not necessary because these answers are always expressed in radians per second. Now, I'm not actually going to work this next one out because after I finally discover this, I guess I should make a comment in the notes one of these days or just get rid of it completely. I finally realized that if you did the rate of change of the other angle, I called it alpha right here on the x-axis, and I think this is always going to be true unless I'm wrong. But I worked it out here. But see, look at the answer. I don't think that was a fluke. I'm pretty sure that these are going to be opposite every time. So that one just turned out being negative 0.5 radians per second. But I'm going to say one more thing about this top one. So you notice as the ladder's going away from the wall, that angle is getting bigger. So that's why it's positive. But then you see that this angle, as the ladder goes away from the wall, that angle alpha is getting narrower. So therefore it has a negative rate of change. But I haven't actually looked at trying to prove this or anything, but I think I worked another example one time and it happened that they were opposite again, so I was pretty much convinced that was true. So, alright, okay, you don't have to be a baseball expert. Don't worry about that. You're going to have to know anything about baseball to solve this next problem. The explanation in a picture is sufficient enough, I think. So, if I ever asked this kind of problem on a test, I would provide a diagram like this with all the bases and everything. But your standard baseball diamond goes like you have home plate at first, second base, third base, back to home, and the player runs counterclockwise. Like, see that? If I can make that a different color, we can see it better. It's coming along, you go to first, you go to second, come around, you go to third, then you come to home. Like that. Alright, so that's all you need to know about baseball for this problem. 90 feet, it's 90 feet distance between each base. So this one's saying this player is running from first to second at a rate of 25 feet per second. So that's the rate of change that they're moving. Find the rate at which the distance from home plate, right here, to the runner is changing when the player is 20 feet away from second base. Now this is a little bit tricky, not that bad for calculus students, but a little bit tricky if you weren't, because you see that 20, you think you're going to be using the number 20, but you're not actually going to be using 20 here. Because so let's look at the triangle I drew here. So there's my x, y, z. So it's going to be your basic x squared plus y squared plus z squared. So this is the trick. I was saying the tricky part. They're saying you're 20 feet away from second and it's 90 feet long. We're more interested in how far we are away from first. So it could have been made a little bit easier if they would have said the runner is 70 feet away from first base, because that's the number we're going to be using here, is 70, not 20. So we have to take 90 minus 20. Okay, so it's a little tricky, but that's important. That's 70. All right, so let's see if are there any variables that aren't changing here? Okay, then there's one variable that's not changing. There are some right triangle problems I've seen where all the variables are changing, so nothing is zero. Like I've seen one where it talks about two planes flying 90 degrees away from each other, the opposite 90 degrees apart, and measuring the distance between them as the hypotenuse. And therefore, in that kind of problem, everything would be changing. The plane's rate of change would be changing, and that distance. Now, unlike the latter problem, the dz dt is not zero because that runner's running from first to second. That's absolutely changing right there, home plate to second base. But the variable that does not change in this particular problem is x, because as the runner is moving from first to second, that's changing. From home plate to the runner is changing, but the distance from home plate to first base is a constant 90 feet, so that never changes. So look at this one. So you see I zeroed out dx dt. Sneaky, huh? The ladder is always the zero dz dt, but okay, this one dx dt is zero. Okay, I got rid of the 2's. I didn't have to. But we still need the Pythagorean theorem to get the z, because we know that it's 90 feet across, 70 feet up. So we need to know what's that hypotenuse. It didn't work out to be a nice clean number there. That's okay. So 90 squared plus 70 squared equals z squared. And solve that, it's approximately 114.202. As you can see what I did in the calculator over there to the right. I took the square root of 90 squared plus 70 squared, which by the way is not the same thing as 90 plus 70. Yeah, that really annoys me whenever somebody says the square root of a squared. This is really hard with a stylus. Yeah, when they say that this does not equal a plus b, that's really frustrating when people do that. Frustrating to me. No, that's bad algebra right there. That is not true. But you see, I put it under the radical, and then it goes, I got 114.02. Now we're in good shape. Now, 25 feet per second running away from first base, that means that's an increasing rate. So his distance is increasing, so it's positive 25. So it's y, which is 70, times dy dt, which is 25, plus 114.02, which is the z, and our unknown is dz dt. Find the rate at which the distance from the runner is changing. All right. And pretty easy algebraic equation to solve. So that distance from home is changing at a rate of 15.35 roughly. There's whatever rounding is necessary. We'll just do whatever is needed. So yeah, so it's 15.35. And there you go. How about that? I'll toss an angle problem in there. Find a rate of change of the angle formed by the first baseline and the distance between the runner and home plate. So as he's running from first to second, we're trying to figure out what that angle is right there, the first baseline and the distance between the home plate. Now, this time I did use tangent. I was explaining earlier that tangent would not have been a good choice for that latter problem, but here it's an excellent choice because you want to use that fixed rate of 90. Now, of course, you could do hypotenuse over opposite, which is secant. You could also do secant here if you wanted to. Problem with secant, you have z over 90, but the problem with secant is the derivative is going to be sec tan, so you're going to have two terms there. It's not that big of a deal, but I like tangent. But the worst one you could use with sine would be terrible. Because sine of theta is y over z. You'd have to use both variables. But you don't want two variables here. You only want one. As long as you have a fixed side, you want to use that. So tangent's y divided by 90, opposite over adjacent, which is 1 over 90 times y again. So it's important that we know the derivative of tangent, of course, which is sec squared. And so it's sec squared d theta dt equals 1/90th times dy dt. So secant is hypotenuse over adjacent, so it's that 114.02 that we found earlier, that's Z. 114.02 divided by 90 squared, and then times d theta dt that we're solving. 1 over 90 is here. dy dt was 25. That was given before also too. So solve that, and we get that angle's changing at a rate of positive roughly 1.73 radians per second. Well, if you visualize that runner from first to second, you can see if it's moving, you can see that angle is going to increase, isn't it? That's the line's going to move that way, and obviously if the runner was running the other direction, that angle would be decreasing. So a positive rate of change makes total sense for this. Here's a fishing line problem. I'm not going to worry about this one too much. The only difference, this one is it's still a triangle, but you have, as you're reeling in the fishing line, that's why it's being reeled in a negative. That's why this is negative, because it's coming in, and the angle is actually increasing, because as the line gets rolled in, it's getting straighter and straighter, which is making the angle larger and larger. So eventually it goes away when it's perfectly pulled in. But I used cosecant on this one just because I wanted to have x over 10. I just called this an arbitrary b length right there. I guess because they had this labeled already as x, I just picked some other letter. Maybe I could use y, I don't know. But it's not too bad, so you just realize that the dx dt is -1, and then these derivatives, and you're in good shape there. Oh yeah, then we had to get what, because it tells us that 25 feet of line at what, so that x is 25, that vertical distance is 10, so you have to use Pythagorean theorem to solve for the b, which is square root of 525, 2291, plug everything in, and that's also an increasing angle, so that's correct. We'd want that. All right, very good. All right, I like this one, the balloon. So I just named this. There's a couple people in my face-to-face class. No, I did not have a student named Bucky, but she wore Bucky t-shirts a lot, so we had fun with it. She liked the nickname Bucky, so we went with that. Let's see. This one's going to be very similar to the baseball player running from first to second, very similar. So we're up in our balloon as it's rising, and the horizontal distance is fixed here at 50. We're using meters, 50 meters. So obviously as the balloon's rising, that's going up. And then of course the z is changing, it's increasing also. Yeah, very similar to that. Find the rate of change in the angle. So we know that it tells us that the balloon's 120 meters above the ground. We know the x is 50. Pythagorean theorem, solve for y. Okay, this one worked out because I used a 5:12 ratio, so 5:12:13. So that one came out unlike the 114.02 in the last problem. That came out as 130. And so there we go. I use tangent. This tangent is good for this one because you can use, even though I have a 120 there, keep in mind you can use 50 because it's fixed here. So I'm just going to erase this for a second so you can see. So really, here's what you're working with technically. And that. So you're working with those three things. Y because it's changing, z because it's changing, x is fixed at 50. I'm using tangent as being y over 50. That's why. And which is 1/50th y. Yeah, very same idea. Derivative tangent sec squared theta d theta dt. So secant would be hypotenuse over adjacent, so it's 130 over 50 squared. D theta dt is the unknown. 150 on the right, dy dt is 4. And that was from, see the balloons rising at 4 meters per second. And then this came out and 0.0118 radians per second. Oh, you see it in the calculator. And I just did this for grams. Normally we do radians per second. You see I multiply by 180 over pi, which that's the conversion from radian to degrees. So it's increasing a little bit less than 1 degree per second. And what are we asking here? Suppose we want to find the rate of the distance from the observer and the balloon is changing with the same dy dt is going up. So we want to find, basically we're looking to find dz dt. At what rate is that length changing? That's then once again, this is similar to the baseball problem, which is what we were finding. So we're trying to find what rate is the distance from Bucky to Crystal changing here. So it's exactly the same idea as that one. So that the dx dt will be 0, because remember that anything fixed, which that distance is fixed, that's not changing. Let's see. All right, so all the x stuff's gone. So we have, I got rid of the 2's. You don't have to, but y is 120. The dy dt is 4, positive. 130 was the z that we found up the last page. 130, and then times dz dt. That's our unknown, so do a little simple algebra. You get 480 divided by 130, roughly about 3.69 meters per second. And that's basically it. I mean, there are just tons and tons of more examples, but you could spend a lot of time on this, but I just pretty much like to keep my questions to these type of problems, and not stray off into kind of more weird, complicated ones. So, well, I hope you found this helpful, and that concludes the lesson on related rates.